to it, man.
So let's see who we got today. We somebody from Toronto Metropolitan University, 520 elite code questions. That's a lot.
Yeah, I've been doing this since first year, so
And what year are you in right now?
I just started third year.
Okay, still early. So what interview do you have? Shopify?
Oh no, no, it's Microsoft.
Ooh, okay. Damn. All right. This is good. This is good then. How you feeling
This
for it?
not too bad. Honestly, like I looked at the tag question, and Microsoft don't ask hard questions, so
Yeah.
fine.
Think it'll be a breeze?
Hey, we'll see.
I mean, let's see where you're at. Like how are you feeling with like a raise, link list?
I don't like linked list, but like I could do it.
Everything's fair game?
Yeah, let's see. Oh, I gotta make an account.
Just put at your name. You don't have to use an account. You just throw a name
Okay.
in there. I think you could just access hop in anonymously.
Oh yeah, we got it.
These are the same type of coder pads you're gonna use in most interviews. So yeah, you need to be able to work with them.
Yeah, you
It's a
see my message?
it's an interactive to code editor. I see exactly what you see. When you
Perfect.
run the code, I see you run the code at the same time. It's pretty live. But do you know what they're gonna ask you? What kind of questions?
Uh, I think basically everything's fair game.
All right, let me run the list and then just ask you frequent.
Sounds good.
What other interviews you got?
I did Bloomberg. I
Ooh,
did my final round
shit.
like 2 days ago, and then
Nice.
I got Snowflake and
Damn, bro, you're
yeah,
cracked. You got all
Snowflake.
of them.
Nah, Snowflake's gonna be tough because these guys are like gonna fry me.
Yeah. So how many lead code questions have you done when it comes? Like, what's the breakdown? Easies, mediums, and hards.
Um, so I was low key. I was just doing daily every day when I was first year, but now I think let me just check actually. Uh, I've done like mostly mediums and then a couple hards, couple medium. Yeah, so like 180, 186 easies, 277 mediums, and 58 hards.
58 hards. Okay, damn. Oh, all right. This is gonna be good. Were you tuned into the stream earlier or no?
Yeah, in the beginning, yeah, I see my boy Ruben, he got
Oh, okay.
Google.
Nice. That's crazy. You know him too?
Yeah. We used to do leak code together
No
2 years ago.
way. All right. Okay. Let me find you a good question, because you're pretty good already. Let me look through my list. Let's see.
Also, could I switch this to Python real quick?
Yeah, yeah,
Does it switch for you too?
yeah. It's good.
Okay,
You
perfect.
haven't used this before?
Not this one exactly. There was something else, but it had like a drawing. Oh, never mind. Yeah, I have used this before.
All right. I'm gonna ask you this question just because I know somebody I know got asked the same question.
Okay, let's see it.
But he was a new grad. But you did a few questions. I gotta ask you something.
Oh, this alien language
Oh,
translate
you already
thing.
done this?
Nah, I probably maybe I don't know. I just like there's so many questions with the language translate. Okay, I'll just start reading it real quick. So it says there's a new alien language that uses English alphabets. However, the order of the letters is unknown to you. You are given a list of strings from the alien language dictionary. I think I've seen this before,
Okay,
but
okay. I'll ask you a different one. Don't worry. Don't even worry. Let's see.
okay. I think I did this like in grade 12. I had an
Holy.
yeah, it was on the exam.
All right. Let's see this. Grade 12 exam. That's crazy. All right. Let's see how you get this question. Some people flop this. All
Okay,
right.
let's see.
You're given a root of a binary tree with unique values and an integer start.
At
And
minute zero.
yeah. Go
Okay.
ahead. Go ahead. Go ahead.
Okay, so it says you are given the root of a binary tree with unique values. Um, okay, and an integer start. At minute zero, an infection starts from the node with value start. Each minute, a node becomes infected if the node is currently uninfected.
Yeah.
The node is adjacent an infected cell. Okay. the number of minutes needed for the entire tree to become infected. Okay, um, so basically, it says this. Okay, it's a binary tree, right? So does that mean that like the values? Wait, let me just reread this real quick.
Yeah.
Each minute a node becomes infected if okay, so the root is infected at the beginning, right? Like just or just start.
Not the
Am-
root. You're gonna be given a node, an integer, start.
Okay, sure.
Let me give you an example. So let's say all the nodes are unique. I think. Yeah, each nodes have a unique value.
Okay,
So you're gonna be given the root of a by. You're just essentially given the root. Let's say it's a node, and a
okay,
start. We're gonna say start is 3.
yep.
Just let me know how long it takes to infect all the nodes if we start at node 3.
Okay, I mean this from what I see here, I'll just write a definition of the method, but just to like see like or the just to get the inputs, I guess. So we call it like whatever. Let's see like how long it takes. Okay, before I even get to like implementing it though. So here we're given 3, right? In this first example. So and the root here is 1, right?
Yeah.
Or we could say 4. Okay, yeah. So when we're given root, we can
Actually, no.
so
This
first we
this
can
tree
just
looks something like this. I'll go in the drawing.
okay, sure.
This tree looks something like this. 1, 3. We go 10, 6. What is it?
Okay, and then our start is 3. Okay.
Yeah. So like pretend our start is 3. How long
Yeah.
does it take to make the whole tree infected?
Yeah, sure. So right off the bat what I'm thinking is, since this is a tree, but it's really not a tree. It's a this is a graph. So what we can do is just create an adjacency list between um everything, right? So we can say that 1 goes to 3, also 3 goes to 1, right? And then 3 also goes to 10, 3 goes to 6, and then 1 goes to 5, 5 goes to 4, 4 goes to 9 and 2, right?
Yeah.
Um so now we can just do a quick literally any graph search here works. So we can do BFS, DFS, etc. Turn this into a adjacency list and then just do level order traversal um over the like what I'm talking about, like first level would be so 3 is already infected, right? So first level would be 1, 10, and 6. We add all the children or all the things adjacent to 6 to the queue,
Yeah.
and then the next iteration, and we just increment the time. And then next iteration, we go to 5, 4, 9, 2, and then that'd be basically the answer.
Sure.
Does that make sense?
Yeah.
Okay, perfect. And let's see. And we just return basically how long it takes for the thing to be infected, right?
Yeah. Exactly. Just an integer.
So should I define a tree node class, or we're just fine just knowing it because like
We let's just say we know it. We don't really need to run
okay,
this.
sure. So here and we take in root start, and then so we can just create that adjacency list. Oh, or let me just from collections import default dict dq. I think for now that should be fine. Okay, so now we're creating that adjacency list. So adjacency list adj is equal to default default dict and then list, and then now we have to do some sort of traversal on this thing. And so one thing here is that regularly they won't a child would not have access to its parents, right?
Yeah.
So whenever we go down, we can just pass the parent like value in.
Sure.
So let's see. So now I'll do def, and then so we're taking in root parent value, or just parent, I guess. And then if not root, we just return, and then we do. Um, so now let's go to that drawing board. So we're at 1. Um, Now we need to add the 2 children. So if it has children, we'll add them to like add the link to it. Okay, so if root dot left, then so we add the link. So adjacent. Okay, adj. Okay, I can't spell. At uh root dot val equals or dot append root dot left dot val. Same thing here. If root dot left or root dot right, adj, yep. And then here we just add the root dot val dot append and root dot right dot val, and then um we can see like and then last one will be like parent, right? But currently there's no parent, so uh if parent, so if the parent exists, then we can just add a connection to that as well. So um
You're just doing a JC root.
append, I guess we could just send in the parent value, right? So okay, and then after we do all this, so here we would be 1 goes to 5, 1 goes to 2, and then 1 goes to nothing else. When we get to 5, we can hold on. We don't have to. Do we have to pass the parent? Oh yeah, we do. Yeah. Okay, so now we can do dfs root dot left, and then root dot val dfs root dot right root dot val. So now okay, let me go through this logic real quick. Just make sure everything's perfect. So we're at 1. We add 5 and 3, and then we add nothing else, right? So then we get to 5. At 5, we add 1 and we add 4. And then we get to 4. At 4, we add 5, and then 9 and 2. And then we're at 9. We only add 4 because there's nothing else. And we get to 2 and we add 4 as well. So does this DFS make sense?
Yeah, yeah. Your
Okay.
DFS makes sense. So you're just
Okay.
building out an adjacency list, so you're converting the tree into a graph essentially.
Yep. So now we can just do
Like,
DFS.
why do we need it as a graph? Like, what's the use of this step?
So the levels here, since the start is not the root, right? So then the levels might not be like starting from the root, right? So then this would be better if and like look pretty. It'd be much nicer if we just do it as a graph, so that for example here when we're at 3, um we can say at 3 time is 0 when we get, and then 1, even though 1 is the root, it's not the first thing to be infected, right? It's the second. So then we need some sort of ordering to go along. Does that make sense?
Mm-hmm.
And then here we can just pass in false, I guess, or I guess none. Yeah. So then now we have that adjacency list, right? Now we can do that kind of level traversal. So yeah. So now we called it. So now you do q equals dq, and then we can pass in uh we can pass in start and 0. So at start, it takes 0 seconds, right? And then we can do while q level equals q dot pop left, and then that would be I guess per point and time. Okay. And then now we get the level size. So level equals len adjacency list at per point. Yeah, so this is how many things it goes to, right? And then you also have to have that like scene, right? So okay. Oh wait, like this needs to be an array. Okay, so with that taken care of, now we have the level, right? So for I in range, and range level, and then we could do like next point. Okay, yeah. So no, we don't actually do this. So we do, we could do adjacency adj at curve point. So this is a list, right? So we could do at index I, and then we could do next point equals that, right? So we're at the next point. Then we can do if next point not in scene. So if we haven't seen this before, then we can just add it to the queue, right? So queue dot append, and then we append per point. Okay, our next point, and then time plus one, and then we just count like time equals 0, and then when we pop something, we can go time equals can't do 2 times, like max time max equals the max of time and max time. Okay. So here we're going through this. Okay, so now I need to add whenever it's not in scene, we need to also add it in scene, right? So scene dot add next point. Okay. So now we add this to the scene, so we will never go over this again, and then at the end we can just return max. Okay, I think for now this is what I'm thinking. Let me know if there's any edge cases or anything that you want me.
Walk me through the DFS or the BFS line by line, starting at line 50.
Line 50. Oh, line 50?
Yeah, like the BFS. I just need to make sure that code's working properly.
Sure. I'll just open up the drawing while
Or
I go
just
through it.
walk through me line by line here. Or
Okay,
I
yeah.
don't need to see the drawing. Yeah, let's just verify
So
the code.
we initialize a DQ,
Sure.
and we add start, which is 3, and time, which is 0, right? So because 3 is infected at time 0.
Yeah.
And then of course, since this is a graph and it's bidirectional, there's bound to be cycles, so we just add the scenes to remove the cycles.
Yeah.
Like we initialize scene, and then we say that we've already seen 3, so that if we were to go to 1, then even though 1 has a link to 3, we've already seen it, so it doesn't matter.
All right.
And then here I'm just initializing a max time, so the max time we've seen, right? So this will be the final thing we return. And then here I do while the queue exists, so while the length of queue is greater than 0, we take the current point, so now it's 3, in time, which is 0, right? So
Yeah.
and then we update max time, and at this point it's just 0, right?
Sure.
and then we find how many things per point um per point has a has a edge to, right?
Sure.
And then so so here we find this 3, right? So for I in range 3, so that uh we're going up till 3, and then um we get the next point. So let's just say here the next point for 3 is 1. So um at the adjacency list at 3, the list like first in or 0th index element is 1. So then we say if 1 is not in scene, then we add it into scene, right? So we have 1 added to scene, and then we also append it to the queue, and then we increment the time because that means that this is like the next cycle, right? Like the next minute,
Yeah.
and then um, that's about it here. And then here these three, 1, 10, and 6 would be added to the
Yeah.
DQ with times 1, 1, 1, and then 10 and 6, there's nothing else that goes to them, so those points won't be added. And then also max down will be updated to 2.
Yeah.
And then at 1, it'll be 3 and 5, but we've already seen 3, so only 5 will get added with time
Yeah. Yeah.
2.
All right.
Yeah, and then
I think you're good. Let's move on to the second question.
sure.
We're gonna stick in the topic of trees, but I'm gonna give you a slightly harder question.
Sure. I applied to that Kleiner Perkins thing you posted as well.
Hey, good luck.
Thanks, bro.
All right, so we're gonna be given an undirected tree consisting of n vertices numbered from 0 to n minus 1. Some of the nodes have apples in those vertices. Just return me the minimum time it takes in seconds to collect all apples in the tree if you start at the vertex 0 and you come back to that vertex. Have you solved this question
Okay.
before?
I don't think I've seen something about apples, but I think it was something else. Okay. I'm gonna go and
This is the
have a
input
read
this
over.
time. Yeah, this is the input changed now. This is
Okay, perfect. So we decide where. Okay, and then okay, the has apples is basically like if index 0 has apples, index 1, etc. Right?
yeah.
Okay, perfect.
Like no node yeah, node 0,
Mm-hmm.
like the index is the node.
Okay, makes sense. Okay, so let me just read this real quick. Given it on the right, the tree consists of n vertices. No, we're okay. Which some have apples in their vertices. You spend 1 time seconds to walk over one edge of the tree. The minimum time in seconds you have to spend to collect all apples in the tree. Starting at vertex. Okay, so like we have to come back to vertex 0, which is like the thing here.
Yeah.
Okay. And then so this then technically it means that for certain like oh wait, did I move something? For certain things, then we don't have to like um even though you're going through a cycle, like it might not like it might be a way back to 0, right? Uh so then you still have to go through it. Okay, this is a little bit more tough than the last one. Um okay. I connect vertices. Additionally, there's a boolean. Okay. So let me just run through this in my head and then
Yeah,
or like
feel free
we'll
to
talk
draw it
about.
out too if you want.
Okay, yeah. So um mm, okay, we need okay, so I mean first year, of course, when we're given like this thing, we can just turn it into a adjacency list again. Um, and we can like do some sort of like uh, I'm just thinking like some sort of like heuristic thing, like only going down a specific path. Wait, this is bidirectional, right? Oh yeah, perfect. Okay, never mind then. Okay, that kind of guarantees that we can reach back to the root, right? So
Well,
that's a good
do you
thing.
understand why the input and output is the way they are? Like why the answer is 8 given that input?
Um, so no, I'll just run through it then. Okay. Okay, so
Yeah.
here 1 goes to 2. Okay, so I mean 0 goes to 1, 0 goes to 2. And but 0 and 1 don't have apples, 2 has apples. So figure out where represents tree red where red has an apple. Okay, wait. So if you go over a vertice, then if you go over the same thing twice, then you you get two apples. Wait, let me draw this out.
Draw out the tree.
Yeah. Okay, so make a circle right here. Let me paste this a bunch. Okay. Like make this this gather drop bigger. Okay, so here this is 0, 1, 2, 3. I just had 7, right? So 4, 5, and then I'll just copy this and just paste it in 2 times. Okay, then 6, 6, 7. Okay. Okay, so it says that 0 has an edge between, and this is a bidirectional edge, so I'll just use this thing. Okay. Okay. And then what's the next? 1 and 4, right? So just put 4 somewhere here. And we put 1 and 4. What else was the other one? Need to make this smaller. Okay, 1 and 5. Let me just move this away. 1 and 5.
Yeah, it's gonna be a tree.
Yeah. Oh, okay, okay. So the input's just different, but it's basically a tree again. Okay. Okay, 1 and 5, and then 2 and 3, right? So 2, 3, and then 2, 6. Oh wait, we don't need this. Oh, okay, it literally is a tree. Okay, that makes sense. Okay, and then so here, 2 has an apple, and I guess I'll use like a
You
like
can
this
mark
thing.
like a different color or something if you want.
Oh, color. Oh,
Yeah,
how?
you can choose color.
Oh, I can add colors. I don't.
Oh,
I don't see it. What number is
or
it
at
as?
the
Oh, wait.
bottom.
Okay. I think no. I don't see anything. I'll just use Oh wait. Oh, okay. I see what it is. Okay. I'll just use light blue to mark that it has a color. Okay. So
That has an
okay.
apple.
Yeah. Yeah. Oh yeah. It has an apple. Okay. So there, 1 has an apple. 2, 3. Okay, and then 4 has an apple, right? Oh. And then okay. I see why it's 8. It's just because um that's how many seconds it takes, right? So and then 4 and then 5 has an apple, is right as
Yeah.
well. Okay. Yeah. Let me just add that. And then so here we have to go to. Okay, wait. Since it's a tree, then we can guarantee there's no cycles. Okay, that makes it much easier. Okay, so here we're starting at 0.
Yeah.
Uh, we can we let's just say we go to 1, right? There's an
Yeah.
apple there. That's time 1. We go to 4 time 2. We go back to 1 time 3, back to 5 time 4, time 5, and then time 6. Okay, so then why is this 8? 1 second. Watch it return them. Oh, wait. I don't. Let me just run through this again. And wait, can I spin this? Okay. Okay, wait, that makes it unclear. Okay.
Yeah, it's harder
Uh
now it's harder to visualize it when it's sideways, huh?
Yeah, okay, let's run through this one more time. So um at 0 it's at okay. So we can say that each edge is like 1 second, right? So here we count 1 second to go to 1, and then we're at 1. Um takes 1 second to go to 4. So that's 2. And we go back and it's 3. And we go to 5. Now it's 4. Now we go back. Now it's 6. And then we go to 0. So it's 7. So
I mean, just draw it out like draw like this is one small tip. Just draw out line 1,
okay.
2, 3, 4, 5, 6.
Okay, but like
Did you mark it
that's
right?
wait, wait, let me check real quick. Okay, 0 goes to 1 and 2. Yeah.
Oh no, 2 has a 0. vertex.
Oh, yeah, 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 yeah. You're right. You're right. You're right. Uh, wait. Let me just erase all this. Okay, well, there we got rid of that. Okay, so 2, 3, 4, 5. So 4 and 5. Okay, the 4 and
Okay.
5 is still fine. So it's just okay. That one little mistake. Okay, let's go ahead and get rid of these.
You still need to go that way though.
Yeah,
But yeah, just
I'm just
go
gonna like
draw it out. Draw it out.
yeah. Okay, which one is the okay? So this is one, and then this has nothing, right?
Yeah.
And then we go 2, 3, 4, 5, 6, 7, 8. Okay, I see it. Okay, so then this is like um um a minimum spanning tree problem that and the only nodes that we need to care about are like are um are the ones with apples, right? Okay. So let's think about this algorithm wise, right? So um we we're at 0 or hmm, okay, this one's kind of tough. Let's see. Uh okay, so I'm sure we still need to turn this into an adjacency list, but like like we can say that we don't need to go to 3 and 4 or 3 and 6, right? Like because they have they have no apples as children, right? So then we can like early that's like optimization. I guess it'll still be O of n, but we can not go down certain subtrees. And I'm just thinking like how would I make sure that a given path is the shortest? Wait, let me do something else. So let's see that instead of going down left, like we go right. Okay, we're at 2. That's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so then it basically doesn't matter which way we go. We just have to do a DFS and only go down to down. We can only go into the nodes which have apples. Does that make sense?
What happens if we go down to a node that doesn't have apples?
Okay, but we'll only go down to a node that has apples if their children are going to be apple, or that doesn't have apples if their children are going to be apples. Like here, if we go to 3, that's just a waste of time, right?
Yeah.
If we go to 6, it's a waste of time. So then there's no point going into that.
Sure.
Okay, so then when I'm building this adjacency list, um, I should like somehow indicate if something has apples or not. Um,
How do I know though that my subtree doesn't have apples?
so so uh so that's what I'm saying. I'm gonna like do do some sort of pre-computation and say that um for example here at 2, we can will return true if anything to the left has an apple, and then or like when we're at 0, we'll do some sort of traversal. Um, I yeah. So then after we do this traversal, we'll check if if any node under 0 has an apple, right? Or under 1 has an apple, and then if it if it does, so when we're at 4, we'll return true, and then when we're at 5, we'll return true, and then we'll only add these as things which are adjacent if they do contain apples or anything under them contains apples. So we'll just do um like false or true or false or true, or like that kind of chaining, I guess. Does that kind of make sense?
Okay. Yeah. I mean, how does that work up to the final solution?
Um, so
Or
so
like, I don't
initially,
get your final solution.
uh, okay,
Or
so what
yeah.
I said right now was just purely building the adjacency list and like pruning the subtrees which don't contain apples,
Sure.
and and then so then we'll have this, right? So okay, wait, I keep on drawing small dots. Okay, this thing and then delete. So we prune 6 and 5, right? Then now we just basically just we can just do a normal DFS and just uh, count. Okay, so then now we have this where we start from 0. We can go down left all the way to 4 and 5, and then when we're coming up, we also add 1, and then we go down 2, and then when we come up, we add 1, and then that way it's over. You
Mm-hmm.
kind of get what I'm saying here?
Yeah.
Okay. Okay, so then should I kind of just start coding in the and of course I'll probably have like more questions or I'll see some
So
more edge cases.
so first you're gonna prune it. So we're gonna know, like, what do you mean prune it? We're gonna know for each node if any of its subtree has an apple.
Yep, that's it.
How are you gonna store that mapping?
Uh that mapping, so it's gonna be like that'll be like pre-computation basically, I'm thinking like
Yeah, like what data structure? Like you pre-compute it, right? What are you gonna
yeah,
store it in? Like
in
how
an adjacency list.
an adjacency list?
Yeah, like the so what I'm thinking is I do some sort of traversal, so um I'll only add like a certain edge if it has children which contain apples, and we can just create like a method like or just a DFS. See, oh, does anything under this have apples? If it does, you add it. If it doesn't, you don't add it to the link. For example, like we go when we're at 2, we say does anything to the left of 2 have apples?
Yeah.
If it does, then we add 2, and then we go to like let's say like or let's say 1. We add 1 and then we go to 5. And we say does anything under 5 have apples?
How would you know that from one though?
So
What if the
so
apple's deeper down the tree than just right under it?
oh no, so I'm okay, can I let's see if I can just delete all of these ugly lines real quick.
Like you're
Okay,
close. I
so
just want to make sure that.
yeah, let me just let's just make this deeper actually. Then we can just move 4 and 5. Uh just say like these both have apples, so just paste that. And then we'll add
Here, I'll make the tree for you real quick.
okay.
So say 7.
I want to track that so it's a little bit of effort. Okay.
Let's do this. Let's say 7 actually has.
Okay, um so whenever we encounter apples, right?
Yeah.
So here at 4 or 5, we're
Yeah.
gonna return true. Okay, so we're at 1. Or we're at 0. I say does the left subtree have apples?
Like what kind
So
of traversal are you doing here?
it's gonna be I don't know the name, but it's like you go all the way to the bottom and then you go back up like um
Post
I don't
order, pre order,
yeah
in order.
it's, I don't know them by name. I
Alright.
just know
Okay.
like just the like it's just 3 combinations of ways
Sure.
you can like
Yeah. Yeah. Yeah.
process them. Okay, yeah. So um we we the main point is we process like the root last, right? So
Okay.
here when we're at 1, we return false or does the let's say like does the right have does the right have a child or a child with apples? Okay, so we go to 8. Like we do DFS at 8 now. Okay, we return another false, and does the child on whatever, like this child 4 have an apple? And we see 4 does have an apple, right? And then there's nothing else to 4. So then uh, we can't go anymore. We return true. And true or false, which is true. So we do add it. Does that make sense?
Okay. All
And
right.
then here,
Okay. Go ahead and implement now.
okay,
Makes sense.
it's kind of a, I don't know if it's like the standard way of doing this, but we'll just like go through and see. Okay, def, and what is this called? Min time to collect apples. And then we're given n edges has apple. Okay. Now we turn this into a adjacency list first. So okay. Now we just go for from to and edges.
Why do we turn this into adjacency list?
So I was gonna just do an adjacency list first,
Okay.
then after that do the pruning for it. Like,
All right.
or let me see if I
That
can
makes sense. Makes sense.
do
Because
the
we're
pruning
given
here.
edges. We're given edges. So
Yeah, like it's just not efficient traversal if it's edges, right?
yeah, yeah. Makes sense.
Okay, so
I
I'll just
thought I
build.
thought for a second we were given the node, but I forgot.
Yeah, I thought it was like it would be more useful if we didn't have it like as a root or something, but okay. Adjacent from oh from dot append to, and then adjacent to dot append from. Okay, now we build that. Now we have to do like step pruning thing, right? So, and we can always just start from like 0, right? Because it's a tree. All right. Root. Okay, and then if not root, return false. And then we do um uh I I guess I'm thinking maybe I just make like 2 adjacency lists because it'll be kind of effort to like update this one after.
Sure, it works for me.
Yeah. Okay. Like um list. Okay. Okay. So now we check if if the root is if the root is has apples, right? So we do if has apples and at index root, then we do uh uh add equals true and and DFS, and since it's a tree we can just do like uh wait, actually this might be like a little weird because I want to go through the subshots only, so you just do like it's like kind of a tree, I guess. Okay, so DFS. Um. Okay, this is kind of okay. If apple is for I in we could just do for I in adjacency at root uh DFS, and then it's like equals false. Like add equals false. So this is like, oh, do we add this subtree? I guess, and then DFS I, and then we also add I to scene. So scene dot add I, and then so here we do add equals true end. Add equals true and that, and then I guess it's, and then if it doesn't have it, so then if has apples at root, if not, or I can just do else. Else, and we do the same thing. So I guess the okay DJ and oh Brian J at root scene dot add add equals, or like, yeah, equals false, or, and then we can do this actually, or too, or DFS
If it has apples.
So that basically what all it changes, like this one condition over here, and then at the end, so this is like when we're at like 4 or 5, right? So we return true if root, if has apples at root, else false, and then here we have to think of like the logic. Okay, prune. Okay, so when we're at 2, has apples, nothing under 2 has apples, so then we don't add it, and then we do if, or if add, so if add is true, then we add it. So pruned, oh, and let me just think.
Like,
Okay,
why
this
is
is
there
like,
a different path for has apple or doesn't have apple?
because this is just the value here. So
Oh, okay.
if the current one has an apple, then we guarantee that it does have an apple, and we go right. Okay, then I think I don't need
I mean,
this.
maybe you could just initialize that here. Like,
Uh, oh, add equals like true if if has apple at, let's see, has apple at root, else false, and then we can just remove this, and then um we can do like, okay, I'm thinking like this, each one is a specific edge we have to add, right? So then and then we also have to check like not going back. So if I not in scene, okay, that's fine. If I, okay, then wait, we can just remove this. and then we
Yeah, like remove
fill.
that whole if.
Yes. If I not in scene, then we add it, and then here we have to have that logic of pruning it, right? So then um then then we do. Actually, I think it's kind of irrelevant if the current thing has it. Now that I think about it, I'll think about it later, like or after I implement this part, right? So here we do the DFS, and we just want to find if okay, and then after we're here, oh that return thing, return true if um has yeah I'm getting a FaceTime. Hold on, let me
It's
just
all good. It's all good.
if has apple at root, else false, and then
Well, you could just
we
simplify that if or just has apple.
oh yeah has apple
So we're at 50 minutes, so I'm giving like slight.
yeah okay, and then we can do the same thing here.
I mean, yeah, okay. What happens? What like pretend we already we know like what are we building here? The pruned? Like where are you changing the pruned?
Oh yeah, I'm gonna do that over here, right? So then um this indicates if any let's see actually. Okay, so when we reach this, we return true. When we're okay, then that means that so then if we do if DFS, so if anything there, if any of the trees under it have apple, then look at this is useless. If anything under it has is true, so it does have apples, then we do um pruned at root dot append I. So then we only add it if it's true. Damn, this low-key took me a while, and it's not that much. Okay, does this make sense?
Yeah. So this has you. Let's say we have the pruned tree. So pruned is just like a. The pruned is just an adjacency list, and all of the edges there are part of this pruned tree. So we're not
Yeah, and
wasting.
we can guarantee that we have to visit everything if we want to get to the final.
Okay,
Um,
so like how are we gonna actually calculate the final result now? Let's assume that we
o-
have this pruned and it's working.
okay, so then we have to do another DFS here. Um, so we go down basically everything, and we add two, right? So like one going down, one coming up. Or wait, actually, let me think if there's like some little bit of a smarter solution here. So we have to go down every edge. Every edge costs two, right? Like
Yeah.
going up and down. So then we can just find the number of edges times two, and then that would be our answer.
Yeah.
Okay, so then um then number of edges are wait, then I think we can just do it some we might be able to do it here. Like okay, we added this, then we can just do like
Well, do we need to know the number of edges or just go ahead?
or like the number of points basically, like these lines.
Vertices or
Yeah,
edges?
yeah,
Okay.
yeah. Okay, so then if this subtree has it, we don't need to add it. We can just do like um res equals 0. So then if this has it, then we must go down it. Then res plus equal 2, or we have to do some like non-local res, and then so then this basically calculates when we go up and down. And then we don't need this. Okay, look, this was not that bad. We don't need pruned. We don't need to add it. We just, I think this should be fine. And then here we just turn res, and we have to call DFS. So D DFS, and it's always at 0, right? Let me just read it. Okay, starting. Yeah. Okay, I think this should be good.
Yeah. Let's see. Let me run it. Let's see. I think yeah, now you got to a solution that's closer to what I was expecting. Let's see. See if it works though. Give me the wrong answer. There's probably like a
The
slight thing to it,
is it
but
off by one or something? Like,
maybe. Like
I think
you
this
returned.
might
Oh, go ahead.
be a little. Pardon?
Like let's see, res. Yeah, let's see. If I is not in C, if I C not add I, yeah, I mean it's kind of wrong because all you're just returning is has apple. Like this DFS is not going to be proper.
Oh, hmm. Wait, is this a medium or a hard?
Medium or yeah, medium. Like you should look at your return there. Is that return proper? Like
Turn has
should you
apple.
should you return if that node has an apple, or should you return if any of its children had an apple? Like what should
Okay,
you return
so
here, true or false?
um, let me just think real quick.
Yeah, I think small modification you'll be able to get it working.
Yeah. Okay, then I guess we do need to check if the current thing we're at is an apple, or or is an apple. So like the add, and then we do um. Okay. Um. So this just returns this has an apple. So it's saying anything under that subtree has an apple. Okay.
Yeah, so for example, like 1 should return true, 8 should return true, right?
Okay. Yeah. Yeah. You're right. So then um we do like um cur equals this has apple's root, and then this could be false or true, and then we have to store if a specific subtree here had an apple. Okay, so then this this will so we say if any had apples equals false. If that's true, any equals true. Return cur or any had apples. Okay, so then I think this might be better.
If not. Yeah, these like small edge cases. If. Just trying to get yours working on my local.
All right.
Oh yeah, okay, I see what you need to change. Ish. Like it's still not gonna work. There's a few things, but or so one thing I'll just point a couple of them out is like if not root, your code will never run because you pass in 0. So if not 0,
Oh,
So you gotta remove that. Like you don't really even need to do that because you're not really gonna traverse. You have an adjacency list that only has edges. It's not like a tree where you're storing null values, so you won't ever get there.
Mm-hmm. Oh, okay. Yeah, you're right. So then I could have just done this with the stack and not.
Yeah.
Okay. Yeah.
You're gonna also another issue is you're adding an extra two at the very end because you call it on zero. When zero returns, it's not gonna be two extra. It doesn't take two extra nodes to visit the zeroth node.
Mm-hmm.
So you're gonna be off by one there, and there's another issue somewhere that I can't figure out yet. But I mean it's close.
Mm-hmm.
But I mean we're at hours. So how do you think you did? How was that?
Um, I think the first one I did pretty good. Like it was, it wasn't that difficult, and then the second one was kind of tough, and I look, you spent too much time on getting that prune thing, like,
Yeah.
and look, it was not like, yeah, I think I needed to think about the approach more from the start before I got to implementing the second one. And also, like I think probably the variable names are pretty bad.
Let's see. Yeah, I think with the first question, that was easy. Pretty strong higher in the first question. No real comments. The only one small nit was, I think, when I asked you why do we need a graph instead of a tree, you didn't really give a good explanation.
Oh, okay.
So I think just like yeah, we need to convert it to a graph because we want to perform a BFS and
Yep.
like we need to be able to traverse when it's a tree, we can't traverse
It's
upwards.
parents, right?
We can't
Exactly.
traverse its parents, so we need to convert into a graph so we can just perform a regular BFS. Um, I forget what you answered, but you mentioned something else. But second question, you took the time to understand I think right away you should have worked through an example to figure out what the question is asking, because you
Yep.
thought it was just gonna be like the second question or the first question, but until you this one you kind of have to draw out the example to figure out why the output is what it is like to understand what the question's even asking.
Mm-hmm. Yeah, that
Um,
makes.
yeah, the solution you're very close to solution. It's a post order traversal. I think you should
Yeah,
understand the names of the different variations as well.
yeah. That's a good thing. I like, uh, sometimes I just forget. I know literally exactly what each one is, but just by name I forget.
Yeah, like pre-order, visit the node first. In order, visit the node in the middle. Post, visit the node at the end. But
Yeah, that makes sense.
like recurs only after you visit every node, kind of thing.
Mm-hmm.
But yeah, I think the second question was close. Yeah, just take a step back, figure out the question. At the end of the day, your solution pivoted from what you initially thought it was gonna be. Like you're not really pruning. You are pruning in a way, but initially you're gonna like prune it and then do another
Yeah,
DFS, but it's
yeah.
complete. Like now you're just doing one post order traversal. So like when I did this question, I was thinking of pruning right away, but then I looked at it and I just thought of a post order traversal similar to what you have here, where we don't have to perform a DFS at the end. So I think yeah, just taking a step back. It's a hard question, but you made pretty good progress on it. So
Yeah, I think this one had a couple of edge cases as well, and I think probably if I spent a bit more time in the beginning, because like just drawing it out, it might have been much easier.
yeah, but anyways, good job. Probably we'll
Thank
probably
you.
give you a pass there on the interview.
Thank you.
All right. Catch you, man.
Yeah, take care, man.
Peace.
Bye bye.
All right, stream. We're done for today. Holy four. That was a grind. Let me record this with my glasses. Christian, what's up? All right, I'm going to go hang out with some friends. Y'all have a good weekend. Thanks for tuning in, like always. Appreciate y'all. I'm checking.